Thanks very much, Andrew, for that introduction. I should say, on top of that introduction, I'm a geologist by background, and the reason why I'm involved with NetZero GeoRDIE is because of the experience I have as a geologist in drilling holes in the ground. So I want to explain what NetZero GeoRDIE is. This is net zero geothermal research for district infrastructure engineering. And again, like the other projects, this is aimed at addressing the goal of reducing the carbon cost of heating and cooling, very much so, but focusing in terms of the project that we're actually doing here to look at how a deep closed loop geothermal system can meet the heating and cooling needs of a modern building. So it takes advantage of the overall objectives of the Decarbonising Heating and Cooling call, and it looks at the infrastructure that we have in Newcastle that enables us to do rather unique research, as I hope you'll see shortly. It's a big team, as you can imagine. So at Newcastle University, it involves myself and a colleague in natural and environmental sciences, meaning the geology. The School of Engineering is heavily involved, and the law school is involved. We have collaborators at the University of Glasgow, led by Gioia Falcone, and at Durham, led by John Glewis. And the point about this is that we can address a number of different aspects in different disciplines. We can look at geology, subsurface energy, energy demand, energy efficiency, and environmental law and regulation. We have a similar portfolio of partners. Local authorities are very heavily involved, and that's not least because the Northeast Local Enterprise Partnership is very active in geothermal energy, and so local authorities are very warm to this, if I might say such a thing. The Environment Agency is involved, Schlumberger, EnviroCentre, which is a consultancy based in Glasgow, GEON and ENGIE as players in the energy space. So we've got a portfolio of partners that covers all aspects of what we're trying to do. The infrastructure that we have is in the middle of Newcastle. We have a new building that was opened, I think, in 2017. I might be wrong there, but it's certainly open and it's alive and kicking. This urban sciences building, Newcastle University put up with a network of sensors, which means that it's instrumented to within an inch of its life in terms of understanding heat flow, understanding use, understanding all aspects of the way a modern building functions. And it is immediately adjacent to the Newcastle Helix geothermal well, which I'll talk about in a bit more detail later, shortly. This borehole was completed in 2014 and proved to be bone dry. So it's one of those embarrassing things where you put down a 2 kilometre deep hole and you can't get anything out of it, and you have to go and tell your Vice Chancellor that the hole is dry, sir. What should we do? And the answer is, as you can imagine, not one that you would want to receive. But it's borne fruit in the end. We have a track record of finding hot water. So this photograph shows me and Paul Younger. Sadly, Paul is no longer alive. But Paul and I were involved in drilling in County Durham, only 50 kilometres from Newcastle University. And we found prolific amounts of warm water at 37 degrees C from a borehole 1,000 metres deep. Warm enough to bath a baby, but there are no babies living near there. So there's no market for that warm water. And that hole is on hold, although people are beginning to look at it again now. That success inspired the funding that we needed to drill to 2 kilometres in the city centre of Newcastle. And the opportunity was taken to work on this demolition site at Newcastle Brewery, where Newcastle Brown Ale used to come from, a large site, 10 hectares, where we were able to drill to 2 kilometres deep in the context of a major urban regeneration project. So that took a lot of time. It was difficult to raise the money, and so it was done in stages, and that's one reason why we had the problems we did. So we started drilling in 2011. A number of things went wrong in 2012 and were put right in 2014 when the 2 kilometre borehole became a 1,600 metre deep well. And this is the interval we're interested in on the left here. We go down to 1,416 metres where the temperature is 63 degrees C, and then we go down to 1,650 metres where it's 68 degrees C. That is in a rock called the Fell Sandstone, and it has lined with this tubing, and you can just about see the drill holes in this tubing. This is put in over this interval so we can take water out of this interval. There are things called packers just above the interval which seal it off, so we know no water's coming down the outside of this tubing to get into it. It can only come from this particular place. And the problem is, of course, that that particular rock doesn't have any water in it. At the top of the well, we have this wellhead, and this is all you can see at the present time. So this is the starting point for the project. That is where we are going to install equipment to extract the heat, as I'll show you shortly. So we encountered the temperatures up to about 73 degrees C in this borehole. And the question is, how can we get the heat out, knowing that there's no water flowing naturally? So our heat transfer fluid has to be artificially introduced into this well to get anything out. And so there are a number of systems where you can do this, which are called single well geothermal systems. Quite commonly, you might have a borehole which has got a concentric set of tubes within it. In this particular case, a central tube which takes warm water to the surface, and around it what we call an annulus, where cooler water goes down, and so the circulatory flow, where heat is flowing from the geological formation across the cement barrier that holds the casing in place into the driving fluid on the well. This is all very well in theory, but the question is, how much heat can it actually produce, and is that enough to support the demand of a modern building? So we're looking at 5 work packages within this: the modeling of the heat transport within that rock mass into the well, what's happening within the well itself, what technology can we use within the well to take the heat out, then how can we integrate the demand that comes from the end user to the capability of that well to deliver at different times of day and at different times of year. Very importantly, to look at the regulatory and legal implications, and to do all this work in the, with stakeholder and public engagement, because obviously this is a high profile activity. So just briefly go over the subsurface modelling and testing, which Joya is leading from Glasgow. Heat transport modelling within the geological formation is then going over into the borehole, where we can monitor what's going on. We can collect steady state data, we can collect transient data, and we can test the models and look at the monitoring of the environment. So that's an important link between modelling and measurement, where there are examples that we can draw from experience: Vegas in Switzerland, Weisbad in Switzerland, Aachen in Germany. These are all very similar wells. Some of them have worked, some of them haven't worked, but that's experience from which we can learn. Each is unique, I should say. So everyone gives a new lesson, and we will be, our system is also unique. But we'll also be thinking about the equipment that can go in the well. We can have a single system of heat flow, like this one shown here, which has got the concentric tubing in the well going through to the heating system within the building, or we can add to it a heat pump as well, and so boost the temperature using a heat pump. So there are a number of different scenarios that we're considering in the modelling of the well design. The testing can be done very simply by circulating fluid and measuring the temperature as it circulates as well. And so in theory, that again is tried and tested. The difficulties which we're still addressing at the moment is the design of what happens within the hole. We've got to get that bit right. So we can monitor the single well. There are various ways of incorporating the telescopic arrangement of the well. It gets narrower as you go down. That has to be taken into account. And it encounters different rock types as you go down. And all these things need to be taken into account and built into the model for the heat flow into the well. So this is the sort of output that we get. This is flow in the well with the cold water coming down, the warm water then rising. So that is one way of that these things come through. And this will then be tied into what Sarah Walker's doing, looking at the building demand for that urban science building. So this is part of an energy system which is supplying heat to a whole complex of buildings. On the site, there will be 10 buildings, each individually designed to the highest of standards, and hence they're described as world-class buildings. There'll be 450 homes. So we know what demand is on the site with 10 megawatts of heating, and we know that it needs 5 megawatts of cooling. We know what the connected power is. And similarly with storage, 8.9 megawatts of heating storage needed, 2.56 megawatts of cooling. and then the equivalent of 300 kilowatt hours of electrical batteries. So it's a very big and complex site, which NG, our partner, is managing. The urban science building itself has got over 4,000 sensors, and it hosts our urban observatory, which if you Google Newcastle Urban Observatory, you can see the data which come from that, which are useful background information. But importantly, this single building has a load of natural gas provided heating of 560 megawatt hours, with average hourly and peak hourly rates known, and then heat pumps again with the power requirements clearly known. And we can try to match these onto what the borehole can supply. So what we're going to be doing is looking at a system whereby we've got the geothermal heat, and through the modeling of the building systems itself, we'll look at what the demand is and sort of work backwards so that we've got two approaches. We've got the geothermal side of things telling what the well can deliver, and the building engineering side looking at what the building needs. And we want to make sure in this project that the two will be able to meet. So in this case, then we expect that the displacement of load with the well might rise up to 78%, depending on the duration of the, as well as the capacity. So just some initial data based on how from the modeling that we've done with a number of scenarios at the present stage, which have got to be tested by measuring. It looks as though a significant contribution can be made to the demands of this building. Pulling the data together, we need to know how it will work, how long it will work, how long that heat resource will last before it becomes unusable, because obviously it takes time for heat to flow to the well. And then what is the cost of electricity to take that heat out of the well? Can we put heat back into the well from the building? And what we want to think about very carefully in the context of this district energy system on the site is it best to connect the well to a single building in a situation like this, or to the district energy system? We don't know the answer to that question yet. Now, just to finish off, and this is not an afterword, this is actually really rather important to get right at the beginning, the regulatory and legal implications of this. We find that when looking at the existing regulatory landscape, that there are issues and uncertainties relating to the definition of heat and coolth. There are also issues relating to ownership, and there are issues relating to environmental implications and risks. So at the moment, this work package is basically defining what these issues are, but through consultation with the Environment Agency as the key regulator in this context, we hope to be able to identify the gaps which become showstoppers in terms of enabling this resource to be used so that can be taken forward. That then enables us to talk in detail with the commercial operations, where we might want to see regulatory incentives being identified, what would be acceptable and interesting to an operator, and where they see the risks as being. It's really important to understand what the commercial risks are for a project of this type, because they can be a big turnoff. And then to learn from experiences in other jurisdictions, such as the Netherlands and elsewhere in Europe and in North America. I've rather rattled through that, but the whole point of this project is to really understand some of the ways that geothermal can be integrated into building design and to de-risk the issue of subsurface assets, because we started this project off with a well which had been drilled at a cost of a few £1 million and was sitting there doing nothing. And of course, there are probably quite a lot of wells sitting there doing nothing that could otherwise be used for geothermal. So we wanted to make sure that this could be a project that would enable those assets to be used, which helps de-risk the drilling project along the line. So it helps create confidence in the drilling community. And it's also important because this whole process is one where we're looking at what is a zero carbon source of energy from underground. If we minimize the carbon cost of moving the water around, then it gives us a very, very strong decarbonized heating and cooling source. I'll stop there. This web link takes you to the project website where you can find out more. And as you can imagine, it's growing as time goes on. Thank you.